Hello, my name is Gutowski and I'm a lecturer in mathematics at the University of Surrey. And what I'd like to talk about today is mathematical proof. And we're going to look at different aspects of this using the square root of 2 to illustrate it. We should be reasonably familiar with the square root of 2, but in fact there are some surprising subtleties. So let's get started. Okay, so to begin with, I would actually like to spend a bit of time just to define what proof actually is, because we need to know what we're talking about. And the working definition for proof is as follows. A proof is a logical argument that shows, starting from definitions, axioms, or other theorems, propositions, lemmas, that a particular statement is true. And just to clarify, lemmas and propositions can be thought of as intermediate steps in establishing theorems. We'll see how this goes when we start looking at some examples. And various techniques can be used in establishing proofs. The ones that we're going to look at here are proof by contradiction and also proof by induction, but there are also others. And we're going to start with an example of proof by contradiction, one which you've probably seen before, which is to do with the square root of 2. And in particular, we're going to show that the square root of 2 is not a rational number. So let's see how that goes. Let's suppose for a contradiction that the square root of 2 is a rational number. Well, what that means is that I can write root 2 is equal to p over q, where p and q are positive integers, and without loss of generality have no common factors, because you can see in this ratio p over q, I can eliminate any common factors by dividing through the numerator and the denominator. So I do assume that there are no common factors because I can get rid of them at this stage. So let's see what I get from this. Well, if I multiply root 2 is equal to p over q through by q, I get the equation p is equal to the square root of 2 times q. And then if I square both sides of this equation, I get p squared is equal to 2 times q squared. So in particular, p squared is even. And we can then deduce something about p from this. Remember that p is a positive integer, so it's got to be either even or odd. If p were odd, then p squared would also be odd, but p squared is even. So p cannot be odd, hence p is even. And that, in turn, means that I can write p is equal to twice m for some positive integer m. Let's now substitute this condition, p equal to 2m, back into the equation p squared is equal to 2q squared, which I had before. Well, p squared is 4 times m squared, so I get the equation 4 times m squared is 2 times q squared. Hence, q squared is equal to 2m squared on dividing through by 2 on both sides. And this in turn implies that q squared is even. Now, of course, I can use the same reasoning as I applied for p in the previous slide. Q as a positive integer must be even or odd. If q were odd, then q squared will also be odd, but q squared is even. So q cannot be odd, hence q must be even. And that's essentially it in terms of the proof. Just to finish it off, I've deduced that both p and q are even and therefore have a common factor of 2, and that's my contradiction. We know that p and q have no common factors, we've already established this, but all of a sudden we've found some common factor, 2. That's the contradiction. So what we've found is that if I assume that the square root of 2 is a rational number, then I get a contradiction, hence the assumption cannot be true, hence the square root of 2 is irrational. And that's it. That's the proof completed. But there is something which I have swept under the carpet. You see, here appears the symbol root 2, and here, and here. And when I write down this symbol, I'm implicitly assuming that the square root of 2 exists. And that's not as obvious as you might think. So what I want to really concentrate on is the issue of existence for the square root of 2. Now that might seem a bit strange. Can't I just put square root of 2 in my calculator and get a number out? Well, sure, you can use a calculator to work out an approximation for a number, but that's not a mathematical proof. And you can actually have certain situations where calculators can mislead you, and there's a link to one of those examples under this video. So let's look at the square root of 2 in a little bit more detail. We know it's not rational, but we do want to establish something a bit more fundamental, which is, does it exist? And to see why that is a little bit subtle, let's just consider the types of properties that real numbers satisfy. Well, they certainly satisfy rules like x plus y is equal to y plus x, and x times y plus z is equal to x times y plus x times z. But those rules by themselves are not sufficient to establish the existence of the square root of 2, because if you think about it, the rational numbers also satisfy x plus y is equal to y plus x, and also this property as well as various other algebraic axioms. And we know that the square root of 2 is not a rational number. So I can't establish the existence of the square root of 2 just by using properties which the rational numbers also satisfy. There must be a hidden property of the real numbers, which is satisfied by real numbers, but not by rational numbers. And this is actually known as the axiom of completeness. Now, I'm not going to discuss the axiom of completeness, but I'm going to use some consequences of it. In particular, I'm going to use two key theorems concerning sequences to establish the existence of the square root of 2. These two key theorems will use the hidden axiom of completeness, and although I'm not going to talk about that, it is actually a key property in proving these theorems. So we're going to assume two key theorems, which are given here. The first theorem is called the monotone convergence theorem, and this is an absolutely key theorem used to establish a convergence of certain types of sequences. And the statement of the theorem is as follows: suppose an is a sequence which is bounded below and monotone decreasing. So bounded below means there is some c such that an is always greater than or equal to c for all n. Monotone decreasing implies that an plus 1 is less than or equal to an. That's the decreasing property. So if I've got a sequence which satisfies this property here, then there exists a real number L such that an tends to L as n goes to infinity. L is then known as the limit of the sequence. So that's the first theorem. The second theorem is to do with limits of sequences where they exist. So let's suppose that an tends to L as n goes to infinity. Well, then there are two key properties. If it is the case that L is non-zero, then 1 over n will tend to 1 over L as n goes to infinity. Note that in this particular case, I'm assuming that L is non-zero. There would be, of course, trouble if I tried to divide 1 by 0. So I'm deliberately excluding that possibility here. So if L is non-zero, then 1 over n will tend to 1 over L as n goes to infinity. The second property is that if there exists a constant k, such that an is always greater than or equal to k, then L is also greater than or equal to k. So these properties 1 and 2 are properties of limits of sequences, provided the limit actually exists. So we're going to use theorem 1 and 2. We're not going to prove them, but the proofs for these theorems are linked to below this video. So let's look first of all, though, at one little subtlety which I've skipped over. I've used an expression an tends to L as n goes to infinity. Now we have an intuitive notion of what convergence is, but we do really need to define what it is. And just for completeness, I'm actually going to give you the definition. You'll see this in any course on real analysis at university. So the formal definition of an tends to L as n goes to infinity is as follows. Given epsilon greater than 0, there exists a natural number capital N, which in usually will depend on the choice of epsilon. So I write n as a function of epsilon, such that for all little n greater than big N, mod an minus L is less than epsilon. That's the formal definition of what convergence is, and I'm just giving it for completeness. We're not really going to use this, but for completeness, I'm presenting it. What this means intuitively is that we can make an get arbitrarily close to L, that's the closeness condition essentially, by choosing small enough epsilon and large enough n. So when we write this down here, we should think of epsilon as being very, very small and n being very, very large. And provided and if this property holds, then the distance between an and L is very, very small. So that's the definition. We're not going to really use it formally, but there it is. Okay, so let's look at the example we're going to be considering. We're going to be looking at a specific sequence, which is this. It's very, very simple. It's given iteratively in this way. An plus 1 is equal to a half times an plus 1 over an, with an initial element a1 is equal to 2. And what we're going to look at first is just look numerically at what this sequence is doing. So we're going to look at some Python code to observe how this sequence behaves. But this isn't a proof of convergence, it's just suggestive. So let's see what we get. Right, so this Python code will print out the first 20 elements of the sequence to a very large number of significant figures. Let's just see what we get. Well, at n equals 6 and 7, it's starting to settle down quite quickly. And by n equals 10, it's not really changing at all to the first 100 significant figures. So it does look as if it's converging, but again, that's just an impression from the first couple of elements in the sequence. We can't deduce mathematically it converges just by looking at this. However, if you take your calculator and work out the square root of 2, you'll get this number. So it's suggestive that it's converging to the square root of 2, but we do need to check this properly. But before we do that, let's look at a more visual representation of the sequence. So this Python code will plot out visually the first 20 elements of the sequence in the two-dimensional plane. Let's see what we get. So this is the first element, the second element. It looks as if it's decreasing, but by the time you're getting to n equals 5, 6, 7 and higher, it's very difficult to discern what's going on because they're very, very close to this blue line. So numerically, it does appear to be converging to this blue line, which is actually the square root of 2. But we do need to prove this properly. So having established that we think the sequence is converging, although we haven't proven it yet, we can work towards a proper proof. And that's actually quite straightforward. Right. So now I want to present the formal proof that the square root of 2 actually exists. Let's see how it goes. I first want to establish a lemma, which is a useful auxiliary result, which I'll use later on in various different ways. So lemma 1 is a statement of a bound. So for all n, an is strictly positive and an squared is greater than or equal to 2. So we prove this statement by induction on little n. So remember, for a proof by induction, I have to do two things. First, I have to check the statement for n equal to 1. That's straightforward. I know that a1 is equal to 2. 2 is greater than 0. So this is fine for n equal to 1. And a1 squared is equal to 2 squared, which is 4, which is strictly greater than 2. So it's certainly greater than or equal to 2. So the statement is true for n equal to 1. I now suppose the statement is true for n equal to k, and I consider ak plus 1 given by my iterative formula here. Well, I know that ak is positive, so that means that a half times ak is positive, and also 1 over ak is positive. So that means that ak plus 1 is a sum of two positive numbers, which is positive. So ak plus 1 is greater than 0. Also, I can compute ak plus 1 squared minus 2 using the formula for ak plus 1 in terms of ak. I expand this out, and then I do some rearrangement of terms, and I find that it's actually a total square, which must be greater than or equal to 0. So consequently, ak plus 1 squared minus 2 is greater than or equal to 0. So ak plus 1 squared is greater than or equal to 2. And that completes my proof by induction. So these bounds here are going to be very useful. But before I use them to establish convergence, I actually want to use them to establish something even more basic, which is that the sequence is well defined. Because these bounds imply that an is never 0. And that's important because remember how I've defined my sequence. an plus 1 is equal to half times an plus 1 over an. Now, I would be in a bit of trouble if there were any value of n such that an were equal to 0, because I would be trying to divide 1 by 0, and that's gibberish. Fortunately, lemma 1 saves me. I never have to deal with this case. An is always strictly positive, and so I'm never trying to divide by 0. The sequence is well defined. It's not going to start being ill-defined at some point. So that's very useful. That's a property of well-definedness for the sequence. So let's now look at convergence. Proposition 1. The sequence an converges to a limit. And I'm going to use the monotone convergence theorem for this. And there are two steps. First, I must establish a lower bound, and then I must establish that the sequence is decreasing. Well, I do actually have a lower bound. An is greater than 0. So that establishes the lower bound. But actually, I do want to sharpen this a bit. I want to get a better lower bound for use later on. So I'll just do that in this proposition because it will be used later on. Because an squared is greater than or equal to 2, and 2 is strictly greater than 1, I deduce that an squared is strictly greater than 1. And that implies this bound, an minus 1 times an plus 1, which of course is just an squared minus 1, that's strictly positive. As an is a positive number, it follows that 1 plus an is also a positive number, so I can divide through this inequality by 1 plus an, and it won't change the order. Consequently, an minus 1 is strictly positive, so an is actually strictly greater than 1. This will be very useful later on because I want to make use of theorem 2, part 2. We'll see how this pops up later. But certainly, I get a lower bound. Good. Now let's take the difference between an plus 1 and an. And to do this, I use the formula for an plus 1 in terms of an here. I rearrange the terms and take out a common factor, and I get 1 over an times 1 minus a half times an squared. Now, remember that an is positive, so 1 over an is positive. And also an squared is greater than or equal to 2, which implies that 1 minus a half an squared is less than or equal to 0. So that means that an plus 1 minus an is a product of a positive number with a number which is less than or equal to 0. Hence, an plus 1 minus an is less than or equal to 0. And that's essentially it. I've now established the lower bound, an is greater than 1, and also an plus 1 is less than or equal to an. Hence, by the monotone convergence theorem, the sequence converges to some limit L as n goes to infinity. The final step is the existence of the square root of 2. Let's now finish off this proof. So now we can prove our final theorem, which is establishing the existence of the square root of 2. And this is the statement. There exists a positive real number x, which satisfies the equation x squared is equal to 2. So x is then root 2. And we've already assembled all of the things we need to do in order to construct the proof. And to do this, we look at our sequence that we've considered. An plus 1 is equal to a half an plus 1 over an, with a1 is equal to 2. We've already proven in the previous proposition that an tends to some limit L as n goes to infinity. We've also established a lower bound for the an. An is strictly greater than 1. And that implies that L, the limit, is going to be greater than or equal to 1 by theorem 2, part 2. Remember that we had already proven previously that an was positive, but what we really want to do is establish that L is non-zero. And establishing that L is greater than or equal to 1 because an is greater than 1 will do that quite nicely. So we've seen that L is greater than or equal to 1, hence L is non-zero, and so 1 over an will tend to 1 over L as n goes to infinity by theorem 2, part 1. So this is the application of theorem 2 here in some different ways. Okay, so we've established these results. Now let's prove the existence of root 2. And that's straightforward enough. We write down the formula for our sequence again, and we take the limit as n goes to infinity in each term. So the term on the left-hand side will tend to L, a half n will tend to a half L, 1 over n will tend to 1 over L as n goes to infinity. So this gives us this rather nice equation, which we can rearrange, take the half L onto the left-hand side, and I'll get a half L is equal to 1 over L, which in turn implies that L squared is 2. Hence, L is a positive real number which satisfies L squared is equal to 2. And I'm done. So this is a little taste of real analysis. We've proven two useful things about the square root of 2. Firstly, and the most subtle issue, is that the square root of 2 actually exists. And we did have to think a bit about that. And secondly, that the square root of 2 is not a rational number. Now, of course, we can continue proving properties of the real numbers, actually making use of some of the things we've talked about here. In particular, you can show that if you have two different real numbers, then it's guaranteed that somewhere in between them, there will be both an irrational number and a rational number. So that's just another aspect of real analysis. And then, of course, you can go on to look at functions of real numbers and properties of them. Then, building on real and complex analysis, you can look at properties of differential equations, ordinary differential equations, partial differential equations, and how these can be used to model aspects of the real world. So there's a whole rich structure of analysis and applications of analysis throughout mathematics. In terms of the material for this video, there are links to the Python files which I use to evaluate the elements of the sequence and plot them out, as well as the formal rigorous proofs for theorem 1 and theorem 2. So those links are attached to this video.